Hello, in the last video we discussed what is union find or DSU and why it is used and some basics. Now let's discuss a question. I will attach the link of this in the description below, read it and give it a try. I will explain the question with respect to example. So this is the original graph and we have some set of bad edges. So for example, if the graph have path between 1 and 5, it is bad, or if it has path between 2 and 6, it is bad, and similarly for all. So if there is a path with respect to any two edges in this, the graph is bad and not good. And we are given q, and it is given that the original graph is not good for sure, is not bad for sure, so it is good initially. And now we have q queries, and for every query we have to add an independent edge, and for every query we have to return the graph after adding this edge is good or not. For example, let's discuss this. For example, we have 2 and 5. So we are adding an edge between 2 and 5. And after that, are there any path from 1 to 5? Yes, there is directly a path from 1 to 5. So there is path between 1 and 5, which is bad edge. So the graph is no longer good after adding this edge. And coming to next query, we have to remove because these are independent queries. So coming to 2 and 6, let's add edge between 2 and 6. And after 2 and 6, do we have path between 1 and 5? No. Yes, we have. No, we don't have path. Do we have from between 2 and 6? Yes. So we have directly an edge between 2 and 6. So there is a path. So even now the graph is not good. And let's add the edge between 2 and 5. Between 5 and 6. So after adding, do we have path from 1 and 5? There is no path. We do not have between 2 and 6 or 4 and 3 as well. So there is no path between any pair in the given bad vertices. So the graph is good, and similarly find for. So for after every query, we have to return whether the graph is good or not. The constraints are n, m, k are all up to 2e5. So firstly, what is the brute force? So simply for every query, add that edge and find whether there is path between any of the bad edges. And if there is at least one path, return 0 because this is no longer a good graph. Else return 1, which is a good graph. And after the processing of query, we can remove the added edge because these are independent. And what is the time complexity? It will be at least q into m, because for every query we are doing BFS or DFS to find whether there is a path. For example, we have added 2 and 5, and after adding, we should go through every bad edge and find whether these two are connected or not by DFS or BFS. So this is not optimal because all are up to 2e5. Now let's try to do a dry run. So let's say these are bad edges, and this is the first query we have to process. So 2 and 5. So let's try to add edge between 2 and 5. After adding this edge, what is the possibility that answer can be no? So the answer will be no if there is at least one path between any bad edge. So let's say this is the connected component 1, which is of 1 to 3, and this is 4 and 5. And now we are adding edge between 2 and 5. So when the answer can be no, the answer will be no only if there is if the 1 4 is a bad edge, or 1 5 is a bad edge, or 2 4 or 2 5, or these two, because we're adding between these two. And after adding, what are the new paths that are formed? After adding this new edge, the new paths that are formed are 1 to 4, because originally we are not able to traverse from 1 to 4, but now because of this new edge, we can reach from 1 to 4 and from 1 to 5 and every other because. So this is the first pair, and this is the second connected component. So after adding edge, what are the new paths formed? We can reach from any node in this connected component to any node in this connected component. So if any of these edges are in the given bad edges set, then it is a bad graph. If there is no path of this in the bad edges, then still it is a good graph. So now what can we do? So we got that if any of these edges are in bad edges graph, bad edges set, then the answer is no. So should we simply traverse every of this and find whether there is occurrence of this in the original one? Should we check every of these edge in the bad edges? Obviously yes, because we have to find whether there is a new bad path formed or not. But should we traverse every of this? So we should traverse one. We should traverse every of this, and we should find whether 1 and 4 in the given one, 1 and 5 in the given one, 2 4 in the given one, and so on. Obviously no, because the time complexity will be more than often for every query. Because, for example, let's assume the size of the first connected component is 1e3, and the size of second connected component is 1e3. And what are the new number of paths formed? It will be 1e3 into 1e3. So we cannot traverse every 1e of 6 in this, and we cannot traverse the set to find whether there is occurrence or not. So obviously we cannot traverse all. And now, can we make this a single one? Because we are going to every of this and we are finding whether this occurrence is there in bad edges or not. But what if we try to make a single one out of this and we just find this in the bad vertices which will be off one or off login? This is very simple, right? So instead of every single edge, what if we try to make whole this a single pair and if we check in the bad edges? And when can we do this? We can only do this if we simply represent a single node with respect to 1 2 3, because we have 1 2 3 here, and if we try to represent 1 2 3 as a single node, then we can try to not traverse the whole thing and we can simply try check this pair whether this is in the bad edges or not. So what I am saying is, let's say we have this all, and instead of traversing every new path that is formed, what if we try to get a single pair and if we just check whether this is in the bad edges or not, then we can get an answer. So we have to represent 1 2 3 in terms of a single node, and similarly we have to represent 4 and 5 in a single node. And when can we do this and how can you do this? So simply we can use DSU here, because in DSU we maintain ultimate parent of every node or leader component. So this is exactly the case that we want here, because if we represent whole 1 2 3 in terms of a single node, let's assume it is 1 and for 4 5 it is 4. So if we represent every connected component with respect to a single node, then we no need to traverse the every new path form and we can simply find the ultimate parent of the connected component, first connected component, and ultimate connected parent of second connected component. So if we check this is in the connected in the bad edges or not, then we can simply get the answer. So we can use DSU here so that our condition will be satisfied, and we can check whether any new path, any new bad path is formed in off login, because we are going to check whether that is in the set or not. So we changed whole list to 1 4 without traversing, without checking every of this to find whether there is occurrence of bad. We can just simply check 1 and 4, because ultimate parent of 1 2 3 is 1 and parent of 4 5 is 4. So now if 1 and 4 is in the bad edges, return no, else yes, because that is what we discussed till now. And is this correct? So let's say this is the old graph, the same graph, and now let's assume these are the ones, bad edges, and now we added between 2 and 5. So what is the new thing that we have to search in the bad graph? It will be 1 4, because we have added edge between 2 and 5, and ultimate parent of 2 is 1, ultimate parent of 5 is 4. So we can just simply check whether 1 and 4 is there or not. So is 1 and 4 present in the given bad edges? No, because we do not have 1 4. So the answer is no, because we have 5 and 1, because for 5 and 1, after adding the 1 and 4, we can traverse 1 and 5 as well. So even now, we have to store the parents in the set. For example, we have 2 6. So in the pair, in the set, we cannot directly add 2 and 6, because we are seeing every connected component with respect to a single node. So what is 2 here? It is simply 1, because it is ultimate parent of 1, because we represent a whole 1 2 3 in terms of 1. So 2 is equal to 1. So add 1 and 6 in the set. And similarly for 4 to 3, ultimate parent of 4 is 4, ultimate parent of 3 is 1. So add 4 1 in the set. And similarly 4 1 in the set. And even now 1 4 is not in the bad edges, but 4 1 is there. So simply for 2 and 6 we can add 1 and 6, because ultimate parent of 2 is 1, ultimate parent of 6 is 6. And we can add 1 and 6 and 1 as well, because then both are same. So even for 4 to 3 we can add 4 1 or 1 4. And similarly for 5 1 we can add 4 1, because 5 1 is 4 1, because we no need duplicates here, because if we have 4 1 2 times, it is useless. We just want whether there is 4 1 or not. So we can simply store all in a set so that we can get only unique elements. So now 1 4 is there in the given. So yes, we got 1 4. So there is bad edge. So the answer is no. So in this way, we can store parent of u, parent of v for every bad edge in the set, so that we can get unique elements. And for every query, we can find parent of u, parent of v. And if this is there in the set, then it is a bad graph, else good graph. So why we use DSU here? Because we have seen that if we try to represent the whole single connected component with respect to a single node, the operation will be simplified. So we use a DSU here. And in the last video, we discussed path compression and union by size, which are the ultimate optimization for finding the union find. Let's discuss the code. we are inputting the n and m, and we are initializing parent of is equal to I, because originally the parent of every node is the node itself, and size of I is equal to 1. We discussed what is size in the last video. So we are traversing the every edge and we are merging those both, and we are traversing the bad, and we are inserting parent of x, parent of y, and parent of y, parent of x to the set, and we are traversing the every query, and we are finding whether find of x, find of y is equal to h dot n. It means that there is no occurrence of that pair in the set. So then the graph is good graph. So print yes, else print no. And why we used find of x, find of y, not parent of x, parent of y. So try to use parent of x, parent of y, and we will get wrong answer, because it is obviously better to check the parent with respect to find of x, because it is obviously log n, and we can update now as well. So hope you understand this. If you have any doubts, comment below. See you in the next video.